Hi everyone, this is our music generation assignment 2 project. For this project, we decided to go with task 1, symbolic unconditioned generation, and task 2, symbolic condition generation. My name is Vincent.
My name's Ethan.
I'm Ava.
I'm Rishi.
So this is an outline of our presentation structure. And for task 1. So for task 1, our objective here is to turn the piano recordings into a supervised learning dataset for our next token prediction transformer. A little bit about the dataset and context. The giant MIDI piano is a public dataset built on classical piano recordings. It contains about 10.8K MIDI files and also from 2.7K different composers. It is sourced mainly from live YouTube video recordings, which are then processed by a high-res piano transcription system that converts the audio into MIDI files. On the right, you can see the license, common uses, and also the GitHub repo if you want to check it out for yourself. For exploratory analysis and data, the first graph we have is pitch distribution. We can see that most of the notes are concentrated around the middle of the piano register. This matches classical piano music where melodies and harmonies are often centered around the playable middle range. An important thing to know is that since high and low notes appear pretty rarely, the model has less training data for those pitches. The second bottom left graph is song length distribution or song length distribution. Most pieces are relatively short to medium length, but some are much longer. Longer songs contribute more examples to the training data relative to the shorter songs. On the top right, we have pitch transition heat map. The heat map shows certain pitch-to-pitch movements that occur much more often than others. And this kind of shows that the data set contains learnable transition patterns. For the last graph, we have next note interval distribution. We can see that the distribution has structure. Something important to note is that the pitches or the pitch jumps are often close to the previous pitch, and this is a behavior that the model can exploit. For this slide, it goes over the data preprocessing pipeline. The first step is to locate the MIDI files. And then after that, we build the token vocab for symbolic MIDI events. In this case, we're using a REMI style event tokenizer. So basically what that means is we represent music as a sequence of discrete event tokens, including position, pitch, velocity, tempo, and other special event tokens. And then we read each MIDI file. Some filters include skipping drum tracks and also only keeping notes that are in the MIDI piano pitch range. Next, we sort notes by start time to preserve the chronological order of music. And then for the next step is our tokenization step. Each music bar is represented by a bar token, where each bar has 48 possible positions, and it's also represented by a tempo token. And then for each note, we convert the notes into event tokens. So each note will have position, pitch, velocity, and duration. Important thing to know is that some tokens utilize bins so that the model can predict categories instead of having to deal with raw continuous values. Each MIDI sequence starts with a BOS and ends with an EOS token. And then we save the tokenized sequences into a pickle file. Next, we create training examples. Token sequences get divided up into chunks. Each example is a input target pair. Input is a sequence chunk, while target is the same chunk but shifted one position forward. And then lastly, we'll split the examples into training and validation sets. So 90% training and 10% validation.
So next is the modeling. So for our task formulation, we're going to treat the music generation as a next token prediction problem. similarly to how large language models work, except for text, we use music. The MIDI file is the input, and it's converted into memory tokens mentioned earlier, where there's going to be 6 consecutive tokens: the position, pitch, velocity, direction, duration, and tempo. And then the model will output a 268 dimension logic matrix representing each token and the confidence about what token comes next. And then we'll optimize this using cross entropy loss against a validation set, like true token. And our baseline will be a first order Markov chain. Some advantages is that it's simple to implement and interpret, and there's no hyperparameters. Some disadvantages that only has a memory of 1 token. Therefore, it can't learn the structure nor the melody of music. And this leads to high perplexity. Some key implementation choices, that's first order type, so we only consider the previous token. And then we use Laplace smoothing, which adds 1 to every transition count, so that the unseen transitions never get a probability of 0. And then our model is going to be a transformer. It attends to all the previous tokens in a 512 context window. And it also learns the distance between tokens using relative attention. And it also scales more with data, and this works for us since we have 10,000 files in the giant mini data set. Some disadvantages is that it uses O of n squared memory. It's also very slow to train, and it requires a lot of hyperparameter tuning. And some key implementation choices is that it's decoder-only architecture, meaning that we use a causal mask so that the model only predicts or see the past token. And then we have relative positional attention as well. And we have repetition penalty, which means that we'll penalize the model for re-looping the same chorus and verses all over again. So then it creates more creativity within the music structure. Next slide, please. So for our architecture, starting from the top, we have the token IDs, and then it goes into an embedding table that maps each of the tokens to a 256 dimensional vector. And then we repeat this, we put it through a transformer that repeats 4 times. And then in our relative attention block, we're gonna have 8 heads, and then each head competes how relevant every previous token is to the current one. And then we'll add a causal mask onto it, preventing any token from seeing the future tokens. Then next, we're gonna have a feed forward network that expands that dimension to 1024 and then go back to 256. And this is basically where the model will learn the musical patterns. And then both of these sublayers use residual connections and layer normalizations to help stabilize the model. And then finally, we're going to output it. We're using output projection to map it back onto the 268 logits. And then at generation time, we'll just apply temperature, repetition penalty, and then top P transformations before sampling the next token. And then we repeat these steps until we get a full MIDI file that we want. Next slide, please. So for our evaluations and results, we evaluated it quantitatively using accuracy, loss, perplexity on a validation set. And qualitatively, we're just looking for correct grammar, rhythmic coherence, and melodic coherence, and physical structure. An important caveat is that perplexity measures the statistical likelihood and not the music quality. So model can hit low perplexity by learning token grammar, but it doesn't understand the harmony or structure of the music. So perplexity is necessary for a good model, but not sufficient. As we can see here, our Markov chain gets a 9.2% accuracy and perplexity of 29.61, whereas our transformer reaches 43% accuracy and perplexity of 5.1. This basically means that our transformer learns way more than our Markov baseline. And as you can see from the graph, at this, it beats it from the start, meaning that there's a large gap between how well these models learn. And this translates to better formatted music, but whether it translates to how better sounding it is objective. But our statistics make a strong case for how our transformer improved upon our baseline, the Markov chain. Next slide, please.
So this slide goes over some related work. So the giant MIDI piano dataset is used primarily to benchmark automatic piano transcription models and also convert audio back into symbolic MIDI. A similar dataset is Maestro, which also contains classical piano-based music. It's also used in a lot of transformer models. Some samples of this data is used in Google's Magenta Music RNN and also the Music VAE. Prior approaches to this task include the Music Transformer in 2018, which is similarly a classical piano transformer trained on the Maestro dataset. And then MuseNet in 2019 was used to scale a GPT-2 style transformer for multi-instrument MIDI. For some similarities and differences, our model architecture is similar to the other models as they're also transformers that use relative attention and similarly large datasets. But due to the differences in resources, our model only has 512 token contexts, 8 layers, and 6 million parameters, whereas bigger models have more model depth.
Next, we're going to discuss task 2, which we use the symbolic condition generation. The dataset that we used, which you can see to the right, is the JSB chorales dataset. You can check it out on the GitHub link. What it is that it's 382 4-part Bach chorales that they're harmonized and they are encoded at the 16th note resolution. It is a very standard benchmark for these type of music modeling. Overall, it has 229 trained, 76 valid, and 77 test chorales. So each of them is around 100 to 500 time steps. That in total gives us around 55,000 something training steps. And this data set is publicly, again, available. So to the left, you can see our task definition, and it's a very simple idea that given a melody, can the model figure out the chords that go underneath that? So at every 16th note, the model sees one soprano note and has to predict the set of notes that are played by the other 3 voices. So the conditioning input is the soprano melody, which is a sequence of MIDI files, MIDI notes, and then the predicted output is the accompanying chords that are represented as a frozen set of MIDI notes. For the EDA, we have more plots on the notebook, but the top 3 are the chord frequency distribution, which is the top left, then the left bottom is the length histogram, and then finally we have the note transition heat map. A couple of things to note about these 3 plots is that for plot 1, there are more than 1,000 unique chords, but as you can see, the top chords are only the 2% of the time steps. So there isn't like a single chord that dominates. So we couldn't really go with the most common chord for prediction. We wouldn't have a valid prediction. The second plot shows that the melody definitely drifts across different time steps. It has different peaks, and however, the whole piece has a shape. And then the heat map shows that nearly anything that is off diagonal is a 0. So that means that our notes mostly never jump. They're actually repetition or they're pretty close by. And then overall for our pre-processing, our data set came pre-split, so there wasn't a manual splitting needed. At each time step, the voice 0 is the melody, and then the others numbered 1, 2, 3 are the chord targets that we want. And then as we discussed earlier, the chords are stored as frozen sets. So if the numbers move, they're still representing the same chord. We put aside the MIDI 0 excluded, so only sounding notes are in the chord. Vocabulary is built from the training set only. There are 24 unique melody notes and overall more than 1,000 unique chords. We have separate placeholders for patching and then the UNK. And at the end, all of these encoded are saved into a pickle file. And to the right, you can see a snapshot of how we parse these chorales. At the end, we take all the pickle file and then implement our model on it.
So when it comes to modeling, we treated this harmonization task as a sequence classification problem where the model reads a given melody and predicts the accompanying chords that are the most fitting. To frame this as a machine learning problem, our input was a melody sequence that was translated into integer indices, and our output was a predicted sequence of chords chosen from a large number of possible chord combinations. We are optimizing this using the cross-entropy loss between the predicted chords and the actual chords themselves. When figuring out the approach we were going to use for modeling, we first built a per note majority baseline. The advantage of this baseline is that it creates a simplified way of matching each note to its most common chord. However, its disadvantage is that it looks at one note at a time and ignores the surrounding melody. To deal with this, we decided on using a bidirectional LSTM model. And the advantage of this architecture is that it captures long-range patterns and uses future melody notes to help predict the current chord. The main disadvantage, though, is that it's somewhat vulnerable to overfitting, and as a result, requires careful tuning and significant regularization to deal with it. Sorry. Next slide, please. Thank you. Looking at our code implementation, you can see our melody to chord LSTM class on the right side of the screen. The inputs, and as you can see, the inputs pass an embedding layer and then feed into the bidirectional LSTM. Because the LSTM processes the sequence in both directions, we have to multiply the hidden dimension by 2 for the linear classification head. To address the overfitting challenge that I mentioned earlier, some of our main implementation choices included utilizing 2 stacked layers, 256 hidden dimensions, a dropout of 0.5, labeled smoothing of 0.1, and performing data augmentation by transposing the music into different keys. Additionally, we also implemented early stopping to further help against overfitting. And looking at the training and validation loss curve on the left side produced by our code, you can see the impact that some of our regularization choices had, rather apparent one being early stopping, which helped to detect when the validation loss started plateauing and stop the training process early. This was done in order to prevent overfitting, which could have continued to worsen if the training had kept going. Next slide, please. For our evaluation context, we had to balance statistical optimization against music quality. The objective optimized by our model which was cross-entropy, relies on an exact match. The exact match is a strict metric that punishes the model, however, if even a single note in the chord is different than from the original chord. However, since music is somewhat subjective, a predicted chord could sound logically connected to the melody even if it wasn't a one-to-one match. This is why we define a good output as one that has chords that simply sound logically connected to the melody and tries to balance the style of the original music without sacrificing much musical flow and harmony. To address this, our evaluation involved implementing 2 metrics, which you could see in the charts. First, we evaluated the exact match. First, we evaluated exact match. Our per note majority baseline scored a 9.91% over, and then our LSTM model scored an exact match of 20.72% accuracy. This demonstrates a clear 10.81% improvement over the trivial baseline. Second, because exact match was too punishing, we implemented a partial match metric. Our code uses Jacquard similarity or intersection over union to see how much overlap there is between the predicted notes and the original notes. As shown in the bar chart, our model hits a 39.13% partial match accuracy. And as you can see, this proves that the model has somewhat successfully learned the underlying musical structure to generate good, logically connected outputs.
And then lastly, for the related work, there are 4 papers that each of them describe partly what we use in our project. The first one being Harmonet. It has the same task with finding the related chords from a specific melody. And the only difference is that this is a very older paper. We currently learned the representation using embeddings instead. The second paper is actually the paper that created this exact data set, which we used throughout the whole project. The third one is closest to us because it also uses an LSTM on the same data set. However, they encode all 4 voices as one stream. However, we explicitly condition on the melody. Last paper also uses a bidirectional and melody condition approach. They use Gibbs sampling at inference. However, we do a single forward pass, which is simpler but also faster. So using different aspects from these papers, we use the same data set, the same task framing as the very first paper, pretty much the same LSTM approach and a bidirectional architecture. And at the end, we also added the partial match that was previously described to increase our exact match evaluation. And that's the result of both of the tasks. We would now like to show you a demo, first of task 1, and then second demo will be for task 2. This is the output of task 1. And the second melody is the output of task 2, which are the chords. And with that, that's the end of our presentation. Thank you so much for listening.